3D object tracking enables continuous, real-time estimation of the 6DOF pose of objects in the real world. It serves as a crucial foundation for computers to understand and interact with the environment. However, most existing methods rely on pre-given model priors or training priors learned from annotated datasets, which limits their flexibility and scalability. In this work, for the first time, we introduce a truly prior-free 3D object tracking method that is both model-free and training-free. We call this method BIT, bidirectional iterative tracking. BIT relies solely on monocular RGB data as input. It consists of a geometry generation module and the pose optimization module. The core idea is to enable these two modules to automatically and iteratively enhance each other, gradually building all the necessary information for the tracking task. The geometry generation module incrementally generates high-precision mesh models for tracking, while the pose optimization module generates additional data during object tracking to further refine the generated models. Moreover, the generated 3D models can be stored and easily reused, allowing for seamless integration into various other tracking systems. Next, let's take a closer look at the detailed overview of BIT. BIT takes RGB images as input, with the first frame utilizing a bounding box to indicate the target object for tracking. Additionally, if available, it can incorporate a limited number of reference frames. After receiving the initial frame, the geometry generation module quickly generates an initial model via inverse rendering and sends it to the pose optimization module. The pose optimization module employs this generated model for continuous tracking. Selecting keyframes from the tracking results and feeding them back to the geometry generation module. The geometry generation module, in turn, utilizes this feedback to further optimize the generated model. These two processes iterate continuously, simultaneously optimizing both the generated model and tracking performance. Once the generated model reaches a sufficient level of precision, only the pose optimization module needs to be executed. The geometry generation module in BIT is designed to quickly generate a 3D mesh model of the target object by leveraging iterative inverse rendering using just RGB images. It starts with the initial frame, the target's bounding box, and pose information, then optionally incorporates masks and bounding boxes from additional reference frames to improve accuracy. The module uses a segmentation method SAM to extract the object mask, then scales and centers it, and adjusts the camera intrinsics K to fit this new mask. Beginning from a simple sphere, we employ the baseline differentiable renderer Softress to inverse render the 3D shape by minimizing a loss function that evaluates how well the projected model matches the provided image masks. Each iteration generates a better mesh model, which is then handed off to the pose optimization module for tracking. The differentiable renderer optimizes scene parameters, such as object geometry, while the renderer itself does not require additional training. Consequently, there is no dependence on training data for its operation. The pose optimization module serves two main functions. First, it uses the generated 3D mesh model to efficiently estimate the object's pose in each frame. Second, it selects keyframes and calculates their bounding boxes, sending both the selected frames and their corresponding poses back to the geometry generation module for further optimization. The method employs a baseline tracker slot for tracking without requiring deep networks or training. To improve model quality and reduce redundancy, it selects keyframes from different viewpoints, only adding a new keyframe if its view direction is sufficiently different from those already chosen. We conducted experiments on both publicly available datasets and real-world scenarios, presenting comprehensive quantitative and qualitative results. On the MOPATE dataset, we adopted the ADDOC metric to assess tracking performance. We tested two versions of our method, R0, which operates without any model or training priors and does not use reference frames, and R3, which also requires no model or training priors but incorporates 3 reference frames. Remarkably, Even without any priors or reference frames, our method achieves superior average performance compared to all other methods. When utilizing 3 reference frames, our method delivers a significant improvement and surpasses all competing methods. During tracking, our method can rapidly generate a 3D model of the target object. To evaluate model reusability, we compared the performance of various trackers using both precise ground truth CAD models and our generated models on the RBOT dataset. We used 3 to 12 reference frames and tracked a small number of frames of the dataset, generating object models. These generated models were then used as inputs for other model-based trackers, which were tested across all frames in the dataset. This setup allowed us to directly compare their performance with trackers using ground truth CID models. The results show that with 6 or more reference frames, our generated models achieve performance very close to that of the ground truth CID models. This demonstrates the effectiveness of our method, as it can successfully transform a model-free tracking problem into a model-based one. We also evaluated our method on real-world scenes, as demonstrated in the video. Thank you all for your attention.